Hello, everyone. Thanks for showing up. My name is Fengwei Zhang. I'm from George Mason University. Today, I'm going to talk about using hardware features for increased debugging transparency. This is the overview of the talk. First, I will start with the motivation of this paper, and then I will talk about background, like a system management mode. Then I will talk about the system architecture, followed by the evaluation results. Lastly, I will conclude my talk with the future directions. Motivation. So the number of malware attacks against computer systems has been increased dramatically. These are some malware attack statistics. Symantec blocked an average of 247 attacks per day. McAfee reported 8 million new malware samples in the first quarter in 2014. In last year alone, malware threats has grown 34% with over 200,000 new threats per day. This is reported by the Kaspersky Lab. Nowadays, computer systems rely on a larger amount of applications to operate, and these applications inevitably create vulnerabilities that could be easily exploited by attackers. Thus, there is a need for us to analyze the behavior of the malware and defend against them. So traditionally, we use virtualization or emulation technologies for malware analysis. And basically, we use virtualization technology to create an isolated execution environment and run the malware inside of the virtual machine, and then run the analysis tool outside of the virtual machine. In this case, analysis tool will be isolated from the malware, and then we can study the behavior of the malware. However, there are some limitations for these traditional approaches. First, virtualization-based approach determine on hypervisor that has a large trusted computing base. For example, Xen hypervisor has about 500,000 lines source code. And the National Vulnerability Database shows that there are about 245 vulnerabilities for Xen hypervisor. Second, traditional approach is incapable of analyzing rootkits with the same or higher level privilege. For example, this approach cannot analyze hypervisor layer or firmware level rootkits. Most importantly, virtualization-based approach cannot analyze ARM malware with anti-virtualization or anti-emulation techniques. So nowadays, malware become more and more sophisticated. So basically, they can use anti-VM and anti-emulation techniques. For example, if a malware finds itself running inside of the virtual machine, it will quit or suspend its own malicious behavior. In this case, the virtualization-based approach will not be analyzed. Last but not least, this approach sometimes suffers from high performance overhead. So in light of this problem, we present a bare metal debugging system called MOUT that leverages system management mode for malware analysis. It basically uses system management mode as a hardware isolated execution environment to run the analysis tool, and it is capable of detecting hypervisor level rootkits. Basically, our approach moves the analysis tool from the hypervisor layer to the hardware, which can achieve a higher level of transparency. Before I'm going to introduce the detail of the system, I would like to give you guys some background knowledge, like system management mode. So what is system management mode? SMN is a special CPU mode existing in the x86 architecture, and it can be used as a hardware isolated execution environment. Originally, SMN is designed for implementing system functions like a power management. So for example, if we fold the laptop goes to sleep, and the laptop may invoke some power saving functions, and these power saving functions could be inside of the system management mode. Also, system management mode has an isolated system management RAM that is inaccessible from the normal operating system. When the normal operating system wants to access this memory region, the hardware will automatically redirect the access to the VGA memory. This is due to the VGA memory has the same mapping with the system management RAM. The only way to enter system management mode is to enter system management interrupt. The next slides, I'm going to talk about the approaches, how to trigger system management interrupt. To exit SMN, we run a special instruction, RSM, to resume the normal operating system back to the protected mode. And note that this RSM instruction can only be executed in the system management mode. So in general, there are two approaches to trigger system management interrupt, software-based and hardware-based. For software-based approach, we can write to a special I/O port specified by the source bridge. For example, Intel chipsets, they use OX2B as a port number. For AMD, they have different port number. For hardware-based approach, we can use I/O devices to trigger system manager interrupt. For example, we can use network card, keyboard, mouse, or hardware timers. And the figure below shows you the steps how to trigger system manager interrupt. The box on your left represents the normal operating system, which is in protective mode. The box on your right represents the isolated execution environment, which is in the system management mode. When the software or hardware triggers a system manager interrupt, the CPU will automatically switches from the protective mode to system management mode. Then the CPU will start to execute a special handler called SMI handler. And this SMI handler is reside in the isolated system management RAM. And this system management RAM is inaccessible from the normal operating system. And at the end of the SMI handler, it will execute the special instruction ISM to resume the normal operating system back to the protective mode. This figure basically just shows you a typical software layers. And from the figure, we can see that the system management mode is part of the BIOS, and it belongs to the firmware layer. I talk about the motivation and the background. So next, I'm going to introduce you the system architecture. As I mentioned, traditional malware debugging, they use virtualization or emulation technologies. So basically, if nowadays malware become more and more sophisticated, if it finds itself running inside of the virtual machine, it will quit or suspend its own malicious behavior. So in this case, traditional approaches will not be able to analyze it. Malt debugs malware on a bare metal machine, and it can remain transparent in the presence of existing anti-debugging, anti-VM, and anti-emulation techniques. The figure below shows you the architecture of the Malt system. The box on your left represents the debugging client, and the box on your right represents the debugging server. And we run the debugged application on the debugging server and use the SMI handler to introspect it. And also we run a GDB like the debugger on the client side. And when the client wants to start a debugging session, it will send a message to the debugging server and trigger system manager interrupt. Then the client will send the debugging commands. And when the SMI handler receives the debugging commands, it will execute the commands and send the response message back to the client. We have implemented a few debugging functions in Malt systems. One of the functions we implemented is the step-by-step execution. And the figure shows you how we achieve step-by-step execution in Malt systems. And basically, we use the performance counter for this purpose. Performance counter is a hardware feature that can count the hardware events. And for example, if we want to implement instruction by instruction execution, we set the performance counter to its maximum value. Then we set the performance counter to count the number of retired instructions. So basically, when the next instruction retires, the counter will overflows. And this overflow action will generate an exception. Then we reroute this exception to become a system manager interrupt. And in this case, we can trigger a system manager interrupt for each instructions. And note that we also can use other hardware events and to implement the different stepping modes. So I talked about motivation, background, system architecture. Now I'm going to talk about the evaluation results. For the evaluation result, we evaluate our system in two aspects: transparency and performance. For transparency analysis, we focus on two subjects. One is the running environment of the debugger. The other is the debugger itself. For the running environment of a debugger, we compare the system management mode with the virtualization and emulation technologies. So in Malt system, we use system management mode, and it is a hardware feature existing in all x86 architecture. While for most traditional approach, they use virtualization and emulation technologies. And they introduce a larger trust contributing base. Also, they introduce a large attacking surface. So we believe that using system management mode is more transparent. In terms of side effects introduced by the debugger itself, in Malt system, we emulate all of the side effects introduced by Malt in CPU, cache, memory, I/O, BIOS, even timing. And also, we show that we can mitigate most of the side effects introduced by our systems. Towards true transparency, Malt is not fully transparent. And for example, it cannot defend against external timing attacks. And we believe that it increases the state-of-the-art debugging transparency. And also, we would like to draw attention to this hardware-based approach for addressing the debugging transparency problem. To measure the performance overhead, we implement a prototype of our systems. The testbed specification shows on the slides. The table shows you the SMN switching and the resume time. So basically, from the table, we can see that SMN switching takes about 3 microseconds, and SMN resume only takes about 5 microseconds. So in total, these two operations only take about 8 microseconds. So it's pretty low overhead. Also, we measure the stepping overhead in our system. Since the SMN is a hardware feature, we measure the overhead on both Windows and Linux platforms. And we use different benchmarks to measure this. And this table shows you the benchmark of Pi operation. So also, we can see that we include 4 different stepping modes. They are file control transfer, near return, taking branch, and instructions. From the table, we can see that if we increase the granularity of these stepping modes, the overhead increases. In conclusion, we developed a system called Malt. It is a bare metal debugging system that employs system management mode to analyze malware. And it is a hardware-assisted system that does not use any virtualization or emulation technologies. And it provides a more transparent execution environment. And also by testing existing anti-debugging, anti-VM, and anti-emulation techniques, Malt remains transparent. So in terms of future work, we would like to combine Malt with other popular debuggers, for example, IDEA Pro or GDB Client. And in this case, basically, we can build a generic interface between Malt and other popular debuggers. And the figure below basically shows you the design of using Malt with multiple other debugging clients. This is a reference. Thank you very much for your attention. I will be happy to take any questions.
Thanks, Fan Wei, for an interesting talk. Questions?
My question is simple. So what's the difference between your work and Bearbox?
I'm sorry, could you repeat your question?
Okay. What's the difference between what's the difference between your work and Bearbox?
I see. So the question is, what's the difference between my work and Bearbox? So as far as I know, for Bearbox, it's also a bare metal malware analysis system. So basically, the Bearbox, they try to focus on the fast restoring. So basically, if you want to debug a malware, you want to start from the clean session, right? And in that case, they try to use the fast way to restart the system. And in our work, we use system management mode. And so basically, in our work, we focus on the transparency part. And in their work, I think we have different focus.
Thank you very much.
Next question.
Matthias Peil, Purdue University. I wonder about timing issues. If malware reads out timing counters or cycle counters and stuff like that, can it observe that you're trapping and resuming all the time?
I'm sorry, so your question is about the timing issue of the system?
Yes, assume the malware executes RTDSC all the time to count cycles that it spent executing, and you're switching back and forth all the time, and if you're single stepping, this will have huge issues regarding timing of the malware itself, and if the malware self-checks itself, it could detect it.
So basically, the question is, a malware can use the timing information to detect our system, since the major contribution of the work is trying to achieve the transparency, right? So for timing attacks, I believe there are two kinds of timing attacks. One is the internal timing attacks, like you mentioned. We can use the RTC, try to check the current time, and to see if there is overhead, means that debugging exists, right? And also another timing attack actually is the external timing attack. So basically, you can send a request to the external server to ask for timing information. So for the internal timing attack, basically in our work, we did like modify those kind of internal timers and to basically mitigate those kind of internal timing attacks. For example, if you execute sometime in the SMI handler, we are going to minus that timing information for the internal timer. But unfortunately for our work, we still cannot defend against external timing attacks, because external timing attacks is very hard to defend, and also the timing information could be encrypted even. So in that case, it's we are still cannot defend against that attack.
Thank you.
Sure. Thanks.
Hi. So on that note, you said the overhead was like 7 microseconds, which you said was very low, but that's like 3 or almost 4 orders of magnitude larger than the time it takes to execute one instruction. So if you're doing that single stepping, you're slowing down execution by a factor of well over 1,000, right? So that doesn't sound like low overhead.
Yes, you're right. So basically, yeah, as I showed in the slides, so there are 2 performance evaluation. One is the SMA switching time, and as I showed in the slides, let me go back for the slides. So in the performance, SMA switching time is pretty low. For each switching, it's only take about 8 microseconds. Like you mentioned, if you do the single stepping, means that every instruction needs this time. And from this, basically, this table shows you the stepping overhead. And we can see that for instruction level overhead, actually, it's about 970 time slowdown. So the system has a very high performance overhead. But the purpose of this work is we are trying to achieve the high transparency. And we do believe there is some kind of malware. They can maybe sacrifice this performance overhead, but the focus of that malware debugging is trying to achieve the high transparency. But I do agree with you, this system still have a very high performance impact.
Thank you.
Trent Jaeger from Penn State. So I've seen malware that takes advantage of, if you're trying to analyze it, say, using GDB, the malware will actually look for the effects that GDB causes to your address space in order to detect that the malware is being debugged and take countermeasures against that. So did you look at your GDB-like debugger and the side effects that it has and whether those are detectable by the malware?
I'm sorry, so I hope I understand your question. So your question is there are some bugs in the GDB, maybe?
No, not bugs. The GDB, the malware will look for whether you're using GDB to debug the malware.
I see. So for our GDB like the debugger, actually, we put most of our code in this kind of isolated execution environment called a system management mode. And this code is inaccessible from the normal operating system. So the malware basically cannot look at the system management on the memory to identify what code is over there. So in this case, we are transparent.
But don't you instrument the malware in order to cause the traps to the system management mode? And that instrumentation could be detected potentially by the malware, and thus the malware would stop. Running.
Right. So in this case, in our paper, we emulate all of those kind of side effects, including you mentioned, for example, we basically introspect the malware. We have to have a mechanism way to set the interrupts frequently, right? Mm-hmm. And also in our paper, we showed how we mitigated those kind of side effects and also those kind of artifacts. And I will be happy to talk about those kind of with you after the talk and regarding to the paper.
Okay, thanks.
Yeah.
So how do you compare the use of SMI with the single-step debugging feature of the Intel processor?
The question is, how can I compare my system with the Intel future stepping system?
Because the processor itself has its own single-step debugging function, right?
So actually, I'm not familiar with the processor single-stepping mode, but I believe if you are talking about the debug register by the Intel chipset, for example, for that debugging register, so basically, if you have ring 0 privilege, the malware can read what's in there, right? And for that purpose, I think the purpose of Intel is trying to, for the debugging function, they are not trying to do the high transparency. But for our system, the focus is to try to achieve the high transparency. And although the debugging function is not as powerful as the Intel debugging function, but I think the two systems has very different focus. I hope I answered the question.
Okay, thank you.
Yeah.
Thank you.